This is the second video of interactive configuration tools, the SolarGen tool. So with this one, we're going to go the next step with a string inverter. We're going to use an optimizer. Now you can use Tigo optimizers with just about any inverter out there on the market. It's a little more difficult to make them communicate. Takes a few more pieces of equipment. The SolarEdge optimizer inverter works with each other. So you have to have an optimizer from SolarEdge if you're using a SolarEdge inverter. So these are two pieces that work very well together, and it simplifies things for you. So this is the example we're using. We have a PV module, a 300 watt PV module, and all we have to do is find an optimizer that matches it in wattage and cell configuration for voltage. So I've selected our module, and it's a Hanwha Q-Cell 300 watt, same as the first example we did in the previous video. We have a huge database. Your module should be in here. If for some reason it's not, you can input your module data up here in the green spaces. Click 0. It'll actually show the module that you put in here if you do that. And all green spaces are inputs. Blue and white are protected, so you can't put anything into those. So once you've selected your module, this data will fill up the blue cells here. And then you can go in and select your optimizer. So like I said, if you're using SolarEdge inverters, you have to use SolarEdge optimizers. And we've selected an optimizer that is in agreement with the PV cell configuration. We have a 60 cell module, and we have a 60 cell SolarEdge optimizer. Pretty easy to pick these. If you were to pick something that did not work, these two voltages did not work with each other, then it would show up over here. You'd see that this would exceed that. So if I used a 72 cell module with this 60 cell optimizer, then it would give you a red warning over here because this voltage would be greater than the 48 volt max. It's unlikely that your voltage would be less than 8 volts. This is a very low MPP tracking for these optimizers. All right, max current output of this optimizer is 15 amps. So for these circuits, once you use the optimizers, the ampacity is controlled by the optimizer, not by the modules. Now all we have to do, once we've matched these two up, is go down and select our inverter. Our inverter is based on the size ratio of the PV array to inverter. And like I said in the previous video, I use 1.25 to 1, 125% greater than the inverter rating. If you look at the inverter data sheets for the SolarEdge, they go anywhere from 135% up to possibly 145 in some cases, which gives quite a large PV array to the inverter. Even with this elevation reduction, it keeps it pretty high. So if you want to go with 135%, as they advertise, and their HD wave inverters are very hefty, they can handle a higher input. It will clip during the spring months when you have a higher radiance and cool temperatures. So you'll lose a little bit in the midday, but maybe the cost benefit is worth it. Anyway, it's up to you. So we have 20.5 is the suggested number of modules that we can use. And this is based on a 1.35 to 1. If I left that at 125, it would pull it back down to 18. So let's go with our original design, and I'm going to be conservative with my designing and not oversized. So we have 18.8, that's 18 modules in the system. We have one inverter, we leave that set. Temperature parameters, -10 and 35 degrees. So these are the same temperature parameters we used in the previous example, and you would want to use the ones for the location in which you're installing this PV array. Now we drop down, and since we have optimizers, the optimizers are controlling the voltage and the current in these strings. and we have certain parameters. If you go to their database, if you go into their data sheets for their optimizers, you'll see the parameters that they can be sized with. And we have this input into our optimizer database. And what we select right here is an optimizer control strings, not inverter control. If we do inverter control strings, we see fewer modules in the string configuration, but allowing the optimizer, which always pushes current and pulls voltage down, we have a lower voltage, and we can put more of these in series. So 19 is the max. Our PV array, as we saw above, it said 18.8, so we could round up to 19 and have one single circuit. That would save us a little time and money, so that's the benefit of having these long strings. So we picked 18, just going with the same model we had before. And we had sort of a trapezoid shape with 8 in the first row, 6 in the second, and 4 in the third. We have one string, 18 and 1, and we tell our drop down here to look at the first column right here. So it pulls the data down, and we have our PV array, the number of modules, the kW rating, and of course, if you drop on down to the bottom page, as before, you can configure this as you wish. And what we have here is a 8, 6, and 4. So we've used all of our modules. It showed 18 we had to have, and we have 0 left over, so we have accounted for them. And we have the configuration. It's a trapezoid shape. Now we can go over to the line diagram, and we're doing the load side. If we did the line side, the only difference is the way this looks. We have the load center for the house and the meter, and then we have the PV array feeding into the line side meter. That's the only difference between these two. Load side, it just shows back feeding into the main panel and then into a bidirectional meter. So we have our module, inverter data, PV array size, and rating of the inverter. Drop down, and we have a single string of 18. So we have the ampacity of a single string, but this is not the ampacity of the module short circuit current. What we have is the max current from the optimizer, which is 15 amps. And so we're sizing our conductors based on the optimizer output, not the short circuit current of the module. So we multiply 15 amps max current times 125%, we get 18.8. So that's our ampacity requirement. Well, if we go down and look at our conductor size, 31015B16, and we see that a number 14 is sufficient on the copper, right? It's 1, 2, 3 columns here for copper, these 3 for aluminum. We're using copper, 90-degree rated conductors, and it's either THHN or USC2 that we're using, and 14 is rated 25 amps, so it is sufficient. We put 14, 25, and the conductor D rate. We only have a temperature D rate. We don't have a more than 3 conductors in a conduit because we only have one circuit. We have 2 conductors. So we have one D rate, temperature is 35 degrees C, and we drop down to 35 degrees C, and in the 90-degree column, it's 0.96. So minimum D rate factor, 0.96. Ohms per 1,000 feet, we pull that up into table 8. And we see that for number 14, 3.14. Right? 3.14. I think our single direction distance was 70 feet. So one-way times 2 is calculated. So we have 1.1% voltage drop, a little less than we had in the previous example. And what is a requirement for our conductor? 15.3 amps. So the overcurrent device would, be 15 amps. And so we just go to 251.22. And number 14. So the grounding conductor is the same size as our conductors. So we have number 14. Then the conduit size. We only have 3 conductors to account for in the number 14. So we can easily put these in to a 1/2 inch. Pull this up a little bit and drop down to our running in conduit. We're going to run THHN, so we can run, it says up to 12 in a 1/2 inch conduit. So we're really good with 3. We do the same thing for the AC side. The ampacity rating requirement, 26.3. So the interesting thing here, this requires a 30 amp overcurrent device. It's the next size overcurrent device. We look in the wrong place here. Let me take that out. 30 amp. So we hover right there and we see the increments. So it goes from 25 to 30 to 35. So we go to the 35 amp overcurrent device. And when we size our conductor, we're looking for 26.3, right? So let's go down, take a look. .3. Okay, right there shows that a number 12 is rated 30 in the 90-degree column. That would be sufficient, except we have an overcurrent device, and this particular table has a reference down here to 244D, and in 244D it states that you cannot protect a number 12 with anything more than a 20 amp overcurrent device. Number 10 can be protected with a 30 amp and no larger. So we're going to have to go to a number 10 conductor because the number 12, although it has the ampacity, 30 amps, cannot be protected by a 30 amp overcurrent device. 20 amps is the max. So we're going to go with a number 10. And what size equipment grounding conductor? This is also a number 10 because the next size overcurrent device is 30. And in our table, it shows that for a 30 amp overcurrent device, a number 10 is the minimum size. So we have everything. The ohms per 1,000 feet for number 10 is 1.2. We just pulled that up in chapter 9 for AC conductors. And number 10, 1.2 right there. Pretty much the same in all these different types of conduit. So we put 1.2, oops, 2, and then conductor length, I think it was 20 feet, what we had in this example. So 0.4. So we have 1.1 and 1.4 is 1.5% voltage drop in the entire circuit. Then we have 4 number 10 conductors. So we'd probably want to do 3/4. I think you can do 1/2 inch. Do 1/2 inch because it allows up to 9. Go back to our conduit fill. THHN, we can put 5. That would be a bit of a tight pull, but you can do it. All right, so your design with the wiring and the current devices and the conduit is finished. Then you just need to do the labeling. So we take 1 through 6 at these positions and take a look at the labeling that's required. Our DC label, it's calculated for you. This comes directly off of the inverter database or data sheet. And the location of the PV source circuits and then DC disconnect is kind of redundant. Usually that's covered in this one label. Rapid shutdown is not required on the DC side because the interactive inverter AC disconnect is what executes this rapid shutdown. So you'd want to have this on the AC side. So let's jump over there to the AC side, and we want to have the AC disconnect labeled with max current and the operating voltage. And then we want to have that rapid shutdown switch over on the AC disconnect. And then, of course, the warning, do not relocate this overcurrent device. If you're backfeeding that main panel and this is a load side connection, then you would want to have that label that you have exceeded the ampacity of the bus bar with the inverter plus the overcurrent device from the main utility coming in. Then, of course, we have a label near the meter stating that there is a parallel producing system. So we want to identify the two sources of power. One is, of course, the utility, and the other is the location of our overcurrent device, or rather our disconnect on the AC side. Then we can go to the generation side, or tab rather, the SolarGen tab. And you put in your solar radiation data for each month of the year. And you can leave this as is if you'd like. The inverter efficiency is kicked in, very high efficiency. 89.7 is the startup efficiency for the system. We put in our cost, our system cost, less the incentives, and gives us a levelized cost of energy. Well, that wraps us up for this video, and the next one we'll be going into will be with the microinverters. Thanks.